So this talk is partly a story of two papers. One of them is physical, intuitive, has nice topics such as the Kitaev chain, Arf invariant topological phases of matter. The other one is mathematical. It uses category theory, graded algebras, super-Wedderburn theorem. As a consequence, it is rigorous, reliable, but also almost completely unreadable. But the two of them are addressing the same problem: how to construct fermionic conformal field theories in two dimensions from bosonic conformal field theories. And, although expressed differently, they have exactly the same solution, which is to take a bosonic conformal field theory, add to it some extra sector, and find a way in which the bosonic CFT consists of bosons and the extra sector consists of fermions, by adding by hand something which makes them fermionic. And indeed, we both add the same thing. However, the motivations of the two papers were quite different. The motivation that Inga Runkel and I had was to understand known models with fermions in, for example, the supersymmetric tricritical Ising model. The motivation of Tachikawa et al. Was to construct new theories from old. So this goes some way to explaining the different approaches. For Tachikawa, it was sufficient to present an idea, a motivation for further study. We already knew what we wanted to study. What we wanted was a great deal of detail about fermionic theories and a way to calculate properly. By that I mean a way to find the data that one expects to have in a conformal field theory, but which, surprisingly, up to last year, apparently had not been found for even such simple models as the free fermion. So, if you go and look in the big yellow book of conformal field theory for the free fermion, you will find, for example, operator product expansions. And these operator product expansions include the building blocks of conformal field theory, which are structure constants. And you can see here that the structure constant C psi sigma mu is identified as e to the I pi by 4 over the square root of 2. But no matter how hard you look, you will not find a structure constants C sigma psi mu or C mu sigma psi. And the reason is not just because the authors of the big yellow book have been lazy. It really seems to be that these have not been written down. And the reason for this really seems to be that before now there was not a consistent calculational scheme in which these could be defined. So that was the principal aim of our paper, to set up a way to unambiguously define a fermionic conformal field theory and to unambiguously define all the structure constants you need, which, as everyone knows, are part of the essential data for a conformal field theory. There was also for us a surprising result which came out of the work, which was that for any fermionic theory, you can construct a new one by changing the parity of a particular sector, the Ramond sector, so that bosons become fermions and fermions become bosons. For the theory studied by Tachikawa, such a relation between two fermionic models was built in from the start, from the way they constructed their models, for which there always had to be a Z2 symmetry. And the effect of this Z2 symmetry was to always create a pair of fermionic models. So this also answered a long-standing question, at least long-standing for me, which was to what extent were superconformal minimum models fully classified. So the original papers go back to 1987, when modular invariant combinations of superconformal characters were classified. So the question is, to what extent does the ability to construct a modular invariant function say that you've found a conformal field theory? The standard construction of a partition function for a theory with fermions involves summing over spin structures. So the spin structure can be plus or minus on either cycle of a torus, and so there are 4 pairs of spin structures. But the last one, often written ZRR, is just the trace over the Ramond sector of -1 to the fermion number, and it is an integer. Clearly the parity shift operation that Tachikawa et al. And we found will simply change the sign of ZRR. And so it's clear that simply finding a combination of characters which gives you a function which is modular invariant is not the same as having found a field theory. The complicated expressions for torus partition functions found by Capelli in terms of characters of the superconformal algebra explicitly make no mention of ZRR. What we've shown is that when ZRR is non-zero, so when this parity flip that changes Ramond bosons into Ramond fermions and vice versa is non-trivial, then the two theories that result are inequivalent. We can show they have different boundary conditions and different defects. So this opens up the possibility of a whole extra layer on what one might have thought was a complete classification of superconformal field theories back in the 80s. But what for me was the real motivation behind this paper was to be able to study boundaries and defects in fermionic conformal field theories without any worries about the things you were talking about were well defined or not. As part of a previous project for the graduate student Isao Makabe, we had found evidence for new exotic defects in regular bosonic conformal field theories through a construction which had an intermediate step with defects, interfaces and boundary conditions in fermionic conformal field theories. And I always had the nagging doubt that since the things we were looking at hadn't actually been studied to the same level of detail, it was possible that the things we were looking at didn't exist, or that there were signs that hadn't been accounted for, which would mean our results were wrong. So what we wanted to do was to put fermionic conformal field theory on the same basis as bosonic conformal field theory, and to my mind, one of the most reliable methods for constructing bosonic field theory is the topological field theory method of Jörg Fröhlich, Jürgen Fuchs, Christoph Schweigert and Ingo Runkel. So it's rather complicated, but that's unavoidable, I think, because it's also mathematically rigorous. And so that's what Ingo and I did. We embarked on the process of working out in detail how fermionic CFTs work in such a formalism. And again, the formalism is now more complicated than it is for the bosonic case because you have to include the spin structure of the surface you're working on, which can be encoded in a network of defects. The upshot is that every field has to have a defect associated to it. And this way you can give unambiguously defined correlation functions in a fermionic theory on a surface with a spin structure. I should point out that the encoding of the spin structure and the basic formulation of a fermionic field theory was already performed by Ingo Runkel together with Novak. What we did was applied in detail to Virasoro minimal models. So let's now turn to one of the main things we studied, which were boundary conditions. At its most basic, a boundary condition is a way to assign correlation functions of fields on a surface with a boundary, such as a disk. We'll assume that there are different boundary conditions. We can label these by A. If we're talking about a conformal field theory, it's natural to require the boundary condition to be conformal. If you just think about the interior of the disk, this corresponds to the action of bulk fields on the vacuum. The boundary condition can be thought of as a boundary state. You take the overlap of the boundary state with the action of bulk fields on the vacuum to get the correlation function on the disk, and so the conformal boundary condition should be in 1-1 correspondence with boundary states. If you know what your boundary states are, they enable you to work out a cylinder partition function. So a cylinder has two boundary conditions. It will correspond to an overlap between boundary states if it is of length L with e to the minus L times the Hamiltonian for the system of size r if r is the circumference of the cylinder. So in this sense, h is propagating along the cylinder. But equally, we can think about a theory defined on a strip with two boundary conditions. There's a Hamiltonian which we can label HAB, which propagates around the cylinder, and the equivalence of these two partition functions says that the overlap between the boundary states should be equal to the trace over the Hilbert space on the strip of e to the minus r HAB of L. So the equality of these two statements is a strong condition on the boundary states. A trace should be a sum over states e to the minus r times the energy of the state, with a coefficient here of 1 for each state. And only certain boundary states will lead to a sum of this form. Furthermore, if you want the boundary condition to be conformal, that will say that this has to be a sum over characters of some algebra, which will an even stronger condition on the form of the states A. So this leads to the so-called Cardi constraint. If you know that your boundary states take a particular form, suppose you know that your boundary state A is going to be the sum over some basis states I with some coefficients BAI, then the constraint that this expression takes the form of a sum will give a constraint on the B's. But there's an alternative way to think about boundary conditions, and that is through the bulk boundary operator product expansion. If we think about a boundary and a field in the bulk, as it approaches the boundary, it should be expressible in terms of fields living on the boundary. So it should be equal to a sum of some structure constants, Ci psi, times the insertion on the boundary, times some known function. It's now very easy to see that the boundary state information is contained in the bulk boundary structure constants. If we think about the insertion of a field on a disk with a boundary condition A, in one limit, as z goes to 0, this will be the overlap of the boundary state with the field phi I. In the other limit, as z goes to 1, this will be a structure constant times the disk with the insertion of the identity field or the overlap of A with the vacuum. So this way we see that information about the boundary states is already contained in the bulk boundary structure constant. And the importance of this is that the bulk boundary structure constants obey independent constraints to the Cardi equation. These are the bulk boundary sewing constraints. Let's start with a situation where we have two fields on the upper half plane and a boundary condition A on the real axis. Now, conformal invariance says this can be expressible in terms of conformal blocks in two ways. By some generalization of the reflection principle, it can be expressed in terms of conformal blocks in one channel and conformal blocks in another channel. So this two-point function, what differs are the channels you sum over and the structure constants that go in front. So here the field I approaches the boundary, the field J approaches the boundary with the identity field in the intermediate channel. Here in this channel I and J approach to field K, so there is a bulk structure constantCijk and then a boundary constant Ck1. Knowledge of the crossing properties relating this basis of functions to this basis of functions gives you a relation that Ci1 times Cj1 will be a sum over K, Cijk, Ck1. These numbers f here are conformal data, part of the model you're considering. So if we neglect this index 1, we have Ci times Cj is a sum over some numbers. Let's just call them Mijk, Ck. At one level, this is a set of nonlinear equations for the constant Ci. At the other level, these are the structure constants of an algebra. So this is called the boundary classifying algebra. If your conformal field theory is bosonic, very straightforwardly, your boundary conditions correspond to representations of the algebra. There's a slight twist on that in the case of fermionic theories, but the exact statement is very similar. So our result on boundary conditions, put most simply, is a consequence of the fact that your fermionic CFT includes a bosonic CFT. And so the boundary classifying algebra for the fermionic CFT includes the boundary classifying algebra of the bosonic CFT. So every boundary condition of the fermionic CFT has to be equal to a boundary condition of the bosonic CFT. And the only extra information you get from having a fermionic CFT is whether the boundary condition has a boundary fermion or not. So in the live session, I will go through a very simple example, probably the free fermion, to show how the classifying algebra method works to find the boundary conditions. You get one of two different answers. You either get 2 boundary conditions or 3 boundary conditions, depending quite what you think the question you should be asking is. That's something we'll be including in a forthcoming paper where we will try to make clear the boundary classifying algebra approach to boundary conditions, because, as I said, I think it's really not very easy to read or disentangle from the paper we wrote last year. There's been some work on boundary conditions, and I think our method is rather better than the ones that have been used. I might try to mention about that. But as it is, I think I'm out of time. I say thank you very much, and I'll leave the rest to the live session.